Hello and welcome to this Design Practice 2 Module 16. I had discussed in great details about some of the materials which are being utilized through the routes of bulk and surface micromachining for realizing the MEMS structures or fabricating the MEMS structures. Today, I am going to just extend this a little further and just briefly summarize some of the silicon MEMS processes. We had already done a review on the polymeric side, polymeric processes, but today I am going to do more on the silicon side. So, this will kind of round off for a designer whatever is needed as an idea who is going to come into MEMS design. Okay. So, let us talk about first silicon and its associated materials. Single crystalline silicon, for example, we know that it has a cubic lattice structure and the silicon is sort of characterized by the crystalline orientation of the corresponding surfaces which are accessed in different directions. The classification is based on what we otherwise know as Miller indices, and it is quite clear here shown in the figure. For example, the 100 direction is corresponding to 1 along the x axis, 0 on the y axis and 1 along 0 on the z axis. That means the direction which is red highlighted in this particular case. Similarly, the 110 direction is a plane indicated by this hatched area right here, where there is both x and y 1 and 1 and z still being 0. So, that is how the 110 direction is represented. So, when we talk about directions in such a orthogonal coordinate system, the Miller indices always show the indicated direction and the indicated plane across which the perpendicular to that plane would be the indicated direction. So, a square bracket such as square bracket 100 in that case is used to represent the direction. For example, coming back here, the direction in which this Miller index is supposed to be 100 is represented by the red arrow, and this hashed plane which is there, which is perpendicular to this particular direction indicated by the red arrow, is actually the plane 100. So, obviously, the parenthesis changes. It is basically the circular brackets which come up for representing a plane which has a primary direction 100 perpendicular to the set of plane, and a set of such equivalent directions are represented by angle brackets. So, basically all such directions of the type square bracket 100 come under the class of angular bracket 100, and all such planes in the direction 100 are represented through circular brackets 100. Equivalent set of planes, if supposing there are more than one such planes representing, they are represented by the third bracket 100. And so, this is how conventionally the crystal direction is recorded when we talk about silicon. One has to understand very well that when we talk about MEMS processes, particularly about fabricating MEMS, it is important for us to understand these directions from a standpoint that tomorrow if some fabrication needs to be carried out in terms of machining always happens in a direction. So, therefore, obviously, we need to know that very well. So, typically when silicon goes out of the foundry, they come as wafers, and the foundry is a process where through a seed crystal you can grow primarily in a certain direction the particular silicon. For example, you can have single crystalline silicon growing all in the 100 direction or all in the 010 direction, so on and so forth. So, what it means essentially is that the seed crystal, the parent crystal which is responsible for the state change is in principle having a plane 100 along the direction of this plane. The growth starts to happen as the seed is taken out from the melt. I am not going into the processing details of silicon because that is another topic altogether, but you can have a pure form of single crystalline silicon by method which is known as the Czochralski's growth method. So, how do you know? How does a person know? Because he is not a witness to what was the seed direction, principal seed direction. So, whenever wafers are taken, there is a taken out or cut or diced, there is a standard norm which is followed by the industry, which is about a flat which is made in the primary direction. For example, this 111p type is indicated by this flat, which means this is a plane containing all the 111 plane, and the direction 111 is exactly perpendicular to this particular plane. So, you have a way to represent, there is an international way to depict all these different aspects in a wafer as it comes handy from the fab to the lab, from the foundry to the fab or the lab. So, there are a couple of other methods which are also used. Zokralkes I already mentioned. So, there is a floating zone method where you do not have any thermal gradients anymore, because so the floating zone method, the polysilicon material is uniformly heated through radio frequency means, so that there are no thermal gradients, and so therefore, float zone methods can result in even higher purity in terms of the structure etc. of the silicon. So, silicon can also be formulated through epitaxial growth or epitaxy. Epitaxy is the single crystalline layer growth from another single crystalline substrate. It is done normally through a molecular beam which prints silicon or silicon molecules, which are made to made to formulate the beam. The most important technique for this epitaxial layer by layer growth is called the molecular beam epitaxy, and the most commonly used, not so precise technique is known as the chemical vapor deposition CVD technique. So, I already mentioned about the molecular beam epitaxy, which is more accurate in terms of putting a few small layers of crystalline silicon of a certain direction on the top of a layer through a molecular beam, which contains typically all these silicon atoms and other species. In the chemical vapor deposition, however, which can be done on large area substrates and which can be used for industry grade fabrication, high yield fabrication, uses a set of chemical reactions. For example, there can be the use of silane or dichlorosilane, as is illustrated here, silane being SiH4, dichlorosilane being SiH2Cl2, where through high temperature and through cracking of this gas molecule, you can generate silicon which is deposited as a solid phase, or maybe silicon chloride SiCl2, and it can further liberate hydrogen in the process. And then again the hydrogen which is excess in the particular chamber because of stoichiometric reasons, again react to SiCl2 and formulate the silicon, an acid residue. So, with the chlorosilane chemistry or with the normal silane chemistry using a cracking temperature of about 1200 degrees Celsius, one can generate solid films, thin films of silicon, and that they are also crystalline in nature. So, epitaxial layers can further be doped by p type or n type material. Okay, for example, if the dopant gases like diborane, phosphine are present in the same CVD system as the silane, so there is a possibility that it may deposit boron defects or phosphorus defects, making it either p type or n type on the single crystalline silicon that has been grown by the CVD process. I already mentioned about the molecular beam epitaxy. The process is similar to an evaporation process using a silicon melt in a crucible, where the entire beam which comes out is made of this beam, so this silicon moieties, and typically the MB is a limited process because of the fact that a high vacuum column would be needed to guide the beam which is being formulated, and that severely limits the substrate sizes etc. So, they are carried out under ultra high vacuum in temperatures ranging from 400 to 800 degrees Celsius, and the process is again the same, a few layers of silicon, pure silicon getting deposited from the beam onto the substrate, which is otherwise a single crystalline silicon. And so, the substrate nature would be reflected in terms of the arrangement of silicon atom, which happens because of deposition through the beam etc. So, there are many other chemistries also associated with CVD. For example, you could have silicon dioxide grown or nitride grown or silicide grown, based on what are the deposition chemistries that you are using. So, this is also very well regarded as an additive manufacturing process, where we are talking about depositing layer by layer of material. Okay. So, this falls under the category of the surface micro machining, as had been illustrated towards the beginning when we talk about such MEMS fabrication. The other form of silicon very commonly available is the polycrystalline form. The name suggests there are multiple crystal centers, and each of them grow, nucleate, and formulate boundaries with respect to one another, and therefore, the polysilicon is considered to be mechanically tougher as a material. Polysilicon can be grown with the low pressure chemical deposition process with either silane or a variety of other gases, as you saw in the last slide. The deposition temperatures for the polycrystalline silicon can range from 575 to 650 degrees Celsius. At temperature below 575 degrees Celsius, the silicon layer is amorphous in nature. It converts its state from amorphous to crystalline beyond 575. The grain size which is typically obtained is about 30 to 300 nanometers, and polysilicon can be doped also, just as you dope the epitaxial silicon. The doping can be carried out again with similar set of gases, diborane or phosphine, and polysilicon typically in surface micro machining is used for giving mechanically stable and robust materials. You saw how a layer was deposited on a sacrificial material, and the sacrificial material removed to create some kind of a small containment, okay, or confinement with the layer on the top. So, it can only be possible if the layer on the top is mechanically robust enough, which can sustain the pressures created because of removing of the sacrificial layer from underneath. So, in microfluidics, the polysilicon can be used for making channel walls and also sealing etched channel structures, and because of the high temperature annealing process, the intrinsic stresses are reduced, and so one can estimate mechanically more robust material, okay, particularly ones which are crystallized at a higher annealing temperature. So, silicon now can be obtained in single crystalline form directly from the growth process, or it can be grown using epitaxial methods, where you have deposition of silicon atom by atom, layer by layer, and then you have the third form of polysilicon, which is actually polycrystalline growth in multiple nucleating centers with grain boundaries, which is mechanically the most robust system of crystalline silicon that can exist. So, that is how silicon can coexist in its different forms. We will now go to, once we have learned about silicon, we go to some of the essential techniques for particularly MEMS applications. So, we talk about subtractive manufacturing or subtractive techniques here. One of the most common techniques being wet etching. So, wet chemical etching is basically the art of engraving into a solid material with some kind of a chemical. The chemical could be an acid, it could be a hydroxide chemistry, and I am going to talk about this wet chemical process in great details. Typically you can categorize the wet etching techniques into either isotropic form or anisotropic form. So, in the isotropic section, we mostly discuss about homogeneous material or material etch processes. Etch rates are similar and not a function of the direction in which etching is taking place. On the other hand, in the anisotropic chemistry, probably depends on the direction which it takes. And so, typically what we do is in microelectronics shield an area and then create a small window or a via through which you can then take the etchant. So, in microelectronics one has to remember that there are two different broad classes of materials when we talk about etching processes. One is known as the etch selective layer, another is known as the material that can be etched. Okay, so, the etch material layer. So, the etch material layer and etch selective layer has a in principle difference, that the etch selective layer is where the etching will stop, okay, as the etchant meets that particular layer or that particular surface, whereas the etch material layer is one where whenever there is a interface of such a layer with the etchant, it starts homogeneously etching out or anisotropically etching out. So, this is the common difference between etch material and etch selective layer. So, you should have for every chemistry that you are using a selective layer and a material layer, and this is how it has been illustrated here. So, the different etchants which are used, for example, a combination of hydrofluoric acid HNO3 and CH3COH can be working on an etch material silicon, but whenever there is a SiO2, this becomes very selective to it and stops the etching process. And similarly, in all these different materials, you can have a common material and a selective material. So, now the advantage is that whenever there is a selective material, you can sort of use it to block the etching process, okay, from carrying forward anymore, and that creates a very big advantage in terms of microstructuring, because let us look at this particular example here, where this material here is a sort of a, you can say, etch selective layer to the particular chemical that is being used. So, what you do is you basically create a via in this etch selective layer and you know, put the chemical in close proximity, so that the moment it touches the layer which is supposed to be the etch material, in this case the layer underneath this particular layer is the etch material. So, it starts etching away, and if it is a homogeneous process and if it is with stirring and all those actions, you may expect that all the vertical and lateral etches are equal to each other, they are homogeneous in all direction, and you will have some kind of a hemisphere emerge because of this etching process. However, if you are not able to remove the material as quickly, there is going to be some diffusional issues, because obviously the walls, you know, or the wall areas are much lower than the, you know, the flat area. That means this particular area, okay, which is subjected to the etch, let us call it the flat area, and so because of which the flat area would have more etching, and if you are not having a removal mechanism, it is going to accumulate the etch particles or etched out particles and create a concentration around the flat, because of which further movement of the etchant towards the flat may be severely limited, and because of which there may be a case of this under etching or lateral etching, you can say, which produces an undercut. So, an undercut typically would happen because of lateral etching. So, if materials are removed properly, then undercut probably happens in a homogeneous manner, but if it is not removed properly, then undercut happens in a very skewed manner, and obviously whatever size or domain you are etching, the overall etch profile that will eventually come out will be higher in size in width than the planned etching zone. So, therefore, masks have to be designed in such cases, and masks, by masks I mean this particular etch selective layer. It could be a resist, it could be some kind of a you know, layer which is selective to a certain etchant, but it has to be designed in a manner so that the via which is there or the opening which is there is not exactly same as the size of the feature that you are intending to obtain, but slightly smaller than that. So, this is how subtractive techniques can be grouped into, or wet etching can be grouped into. This is again another schematic showing the essence of selectivity. So, these are two different examples where you can see a poor selectivity given by the green material right here to a set of chemicals which otherwise etch off the pink material, okay, but the same selectivity being more in this particular case would have a better impact in terms of the formulation of the interface. You can see the overall roughness of the interface formulated here and here are quite different. Here the interface roughness is lower because of the higher etch selectivity that the green layer has to offer. So, this is how etch selectivity is kind of defined. Let us now look into another very important process, which is about how etching can be carried out without wetting agents. Particularly, you know, etching can be carried out with sort of physical particles knocking off material, high energy beams for example, or ions or laser. And I am also going to talk about material where, you know, chemical gases are used for etching in a later on slide. So, essentially what happens in these physical dry etching processes is that there is a lot of kinetic energy which impact the particular surface, because of which there is a transfer of energy to the base material, and a knocking off of the atoms on the surface of the base material, which can be otherwise known as etching. Also, due to certain, you know, energy mode being delivered into the material, there is a chance of conversion of one kind of energy to the other. For example, in laser etching, you use a bunch of photons which have high energy, but the photons are converted into phononic vibrations of the surface bonds. Photons are absorbed within the material, and because of the absorption there is a raise in the temperature or raise in the kinetic energy. So, the mode converts from a photon to a phononic vibration. So, that is how you can use different beams, high energy beams or photon beams, to selectively remove or melt away or vaporize materials. So, the high beam energy then evaporates and knocks out the material. Some of the limitations the process has to offer is that they are extremely slow on the etch rates, because sufficient amount of thermal excitation within the surface layers of a hard material is also a very difficult process. The other issue is a low selectivity. In the wet etching case, you have a complete definition of a layer which is selective to the advancement of etching processes. So, the moment there is a layer like that which comes in the path of the etching, it will automatically screen off the etching completely from going into the areas where they can affect. But here in this case, because of the ion attack and the rebounding of the ions, etc., generally whatever is being attacked by the ion would have some kind of a thermal energy and melting or vaporizing aspect. So, there is not much selectivity unless there is a masking or shielding which is offered through a shadow mask, which I will come to later probably when we do some talking about lithography processes. So, there are these rebounded ions which are or electrons maybe which are able to etch the surface, but not probably to that level of roughness. There are certain trench effects caused by the reflected or bounced back ions from the surface, and that kind of creates an overall higher roughness level. Also, you have to remember, because the material is melting and not getting carried away that fast, there is going to be some kind of recyclement in terms of recrystallization and growth in those areas. And so, therefore, the surface which formulates after the etching is not really very planar in nature, and it has to have some other hybrid strategies coupled for making it planar, like you have a secondary etching step, for example, incorporated in some of these processes. So, and by etching I mean chemical etching, wet chemical etching. So, you have then chemical dry etching techniques, where again there is a chemical reaction between the etchant gas in a manner that it attacks the material on the surface and carries away the material as in gaseous state. So, for example, silicon facing a chlorine gas or a fluorine gas would typically convert into SiF4 or SiCl4, and it can be then carried out, and because both of them are gaseous states, and that way the silicon can go off the atoms of the solid surface. So, gaseous products are conditions for chemical dry etching, because deposition of reaction products will stop the etching process. That is one. Also, chemical dry etching is isotropic. The technique is similar to wet etching and exhibits relatively high selectivity. You can see some of the gases or the gas recipes which are selective again to certain materials and are active to certain etch materials. So, for silicon, silicon oxide, nitride, aluminum, and many organics, you have different etch gases or etch chemistries between gases. So, this is also similar to a CVD reactor, where these gases are sent in at a controlled manner, and they interact with the surface and create gaseous products of material coming off the surface, and thus etch away or engrave the material in the process wherever they are exposed to or wherever the gases can attack. There is also yet another important etching aspect, which is called the physicochemical etching, where there is some physical means of attack by virtue of bias created within a system, and then there is some chemical means of attack where there is a chemical reaction in place. These are known as RIE or reactive ion etching techniques. I will come into some details of this later as we have time for doing some processing for MEMS. There is also anodic plasma etching, there is magnetically enhanced reactive ion etching, triode reactive ion etching, and transmission coupled plasma etching. These are different processes without getting into the details of these are some physicochemical. So, you are using the power of the ionic state of gas, that is plasma, and then on one hand you are creating bias to impact so that the ions can impact a flat surface. On the other hand, you are also creating small amount of chemical reactions with those ions which are impacting the surface then, so that there can be some etching carried out in this manner. So, I think I would like to close on this particular module, but in the next module I will look at another form of etching and some basic lithography and other processes which are important for you to understand before we proceed into how to design sensors and design actuators. So, thank you very much for your attention.